Okay, so don't worry about the 91 slides because there's a lot of stages of the build. So,
91 slides, really?
Well, it's
no,
okay.
no, it is
At
PDF
45
files.
seconds a slide, so on the other side.
Yeah, yeah, no.
How many slides?
Maybe.
No, in the PDF files, no. But I think maybe something like 30 or something.
Like 50 less than Brodsky.
No,
No, Brodsky is 150.
Sure, good advice. We had to talk like that because of some projector issues upstairs. We were two at a time, side by side.
Anyway, so my talk will be about Gluon TMDs in EA, but not all the time EA. So some things will possibly EA and so on. Yeah, so this is sort of the topics I will cover. So Gluon TMDs and their inherent process dependence. I will take an example of the Simmers effect, which is a polarization effect. So maybe not all of you are equally interested in polarized things, but it is a good example to illustrate some things. And yeah, so I will come to the unpolarized cases where the hadron is unpolarized. So I will consider a small X limit, Wilson loop matrix elements, unpolarized Gluon TMDs, linear polarization gluons, and then go to G TMDs and mention some other things. Yeah, so let me go to the Gluon TMDs. So TMD is a transverse momentum dependent distribution function, and they're typical processes where you probe these things. So the quark TMDs are typically probed in semi-inclusive DIS, like this. And for instance, Gluon TMDs are probed in a process where you do open heavy quarks, so CC bar or BB bar. So those are sort of the typical processes. The correlator that is probed for these gluons is the following. So it is written in terms of KT. Yeah, sometimes I call PT. I haven't done this consistently. So this is just the gluon transverse momentum. So this correlator depends on X and KT, and it has two indices which are transverse in the leading twist at least. So I will do everything leading twist. And so it's a Fourier transform of this matrix element here, where you have two field strength tensors at different positions, and therefore you have two gauge links in between. So U and U prime. And you can parameterize this in tensor structures. And for an unpolarized proton, you just, with the leading twist, have just two functions. So this is the unpolarized Gluon TMD, also called G of X KT. That's a familiar one, I think, for most people here. And there can be this other thing, which is a TMD of linearly polarized gluons. So inside an unpolarized proton, there can be linearly polarized gluons, as long as they have transverse momentum. And so that's essential. And you see here this rank 2 structure. So if you integrate over transverse momentum, this averages out.
I thought you introduced
that. Not for gluons.
Not for
The example that I will look at first is this, the one where the proton is transversely polarized. So this is the Gluon Simmers TMD. So we have a proton moving in this direction. It is transversely polarized in this direction. And then this effect says, okay, the gluons prefer to have momentum to the left or to the right. And actually, we don't know yet because this thing has not been extracted from an experiment. But it can be there. So if you have the proton momentum, transverse spin, this distribution, the transverse momentum distribution can be left-right asymmetric without violating any symmetries of QCD. It comes with one factor of transverse momentum. If you integrate over it, it is gone. Yeah, so those are the three TMDs that we will discuss. There are other TMDs, but so leading twist, there are 8, but it's more of the same. Yeah, this I use for illustration, and then these are the main topic. So let's first look a little bit at this inherent process dependence, as I said. So you have these different gauge links here, U and U prime. Your path ordered exponentials like this. And you have here the case where the different positions are not just separated in the light cone direction, but also have some transfer speeds. So you can actually go in infinitely many ways from 0 to this point. And it turned out that the gauge link shape depends on the initial and the final state interactions in the process. And this was known actually for quite some time. But for a long time, people thought this has no consequences because you can always think, okay, I take a gauge and this thing becomes unity. And if it's unity, I cannot feel it. But that turned out to be wrong. So it has observable effects, as was first shown for these quark-Sivers symmetries. And later, it was realized in the small x context by Cyril and collaborators that it actually also affects unpolarized Gluon TMDs. So in the quark-Sivers case, so if you look in semi-inclusive DIS, you get this what's called a plus link. This probably heard it 100 times by now. So this goes along the light cone to plus infinity, and then in the transfer speeds, the transfer direction, and then back. And in Drell-Yan, you would have the pass pointing Wilson line, and you can relate those by parity and time reversal transformations, such that the Sivers, quark-Sivers in semi-inclusive DIS has the opposite sign as the one in Drell-Yan. So in this, I think, there's an important insight with John Collins that actually the gauge links have observable effects. And you can have a similar thing for gluons, but there are two gauge links, so you have more possibilities. But the two cases that I will look at, is for all practical purposes, we only have to look at two cases. That is the one with two plus links and the one with the plus and the minus link. Because minus minus and minus plus are related. And the more complicated paths, where for instance this one loops around once more, they appear in processes where we don't even know if they are TMD factorizing. So if we stick to the TMD factorizing processes that we know of so far, only these two cases are important. Okay, and just to show you that it really has an effect on the functions. So you can define a particular, you can take Mellin moments of the TMDs, and you can take sort of Bessel moments to make it convergent. So yesterday there was a discussion about the average KT squared. That's of course usually not convergent, but you don't have to take actually just the integral with KT squared. You can also put some Bessel functions there and expand in those things.
So just take KT.
Or KT, but you can also do just anything that's, but Bessel, weighting with Bessel functions turned out to be very nice. Because it relates to some moments that were defined earlier. Doesn't really matter. But so instead of the Sivers TMD, so you take some integrals of it and you get what's called a Sivers shift. So the average transverse momentum shift orthogonal to the transverse spin. And so this is well-defined quantity, finite everything, and could be evaluated on the lattice. And actually, when we were defining this thing, Bernie Musch was at the same time, without telling us, calculating it on the lattice. So actually, when we had finished the paper, he immediately had the results. So it was an interesting way of collaborating. So what was the result? Was this, that if you take the Sivers shift with gauge links, set to the plus link, and now as a function of the extent in this direction, so you start to slowly go from here, make it shorter and shorter, so you go via the straight link and go into the Drell-Yan link. So here's the Sivers link, here's the straight link, 0, and here's the Drell-Yan link. And it is clearly non-zero when you don't have the straight link. And I think this is the first principle demonstration within QCD. Brodsky always says, well, in QED we already knew it, that it's non-zero. But in QCD, so that the Sivers TMD is really there, is non-zero for staple-like links, and it shows this sign change relation, which is actually clear because they use the definition that has that property. It doesn't mean that in experiment you will actually find a sign change. Yeah, but this shows that the gauge links have observable effects. So this is, yeah, they matter. Okay, so for the gluon sievers, you have two options. So, for instance, at EIC, you could do this process, open heavy quark production. You probe the one with 2+ links. And at RIG, in certain kinematic regime, you can do double photon production. That probes the ---- link. And ++ for this Sievert's case is minus the --. And therefore you get this relation between these observables, and this you can do at EIC in principle, and this you can do at RIG. You can test whether this also applies in the Gluon case, which I don't see any reason why it shouldn't, but you never know. So there was a recent paper studying this for EIC, and it turns out this is very challenging, if not impossible. Digest is better, but then it's theoretically less clean, so there's always this trade-off. And for RIG, this is also not very easy. But in principle, there's such a relation. But you can also do, instead of 2 photons, you can do photon jet, and then you probe +-, so this +-, which is related by PT to the --+. So that's a completely separate quantity. Yeah, so it gives you, so there are 2 distinct, independent Gluon TMDs. And if you take well, some transverse moment, it's related to the FABC and the ABC color structures. Yeah, so that's not, that would be nice that is tested to see that these functions are actually different.
My last question, there are still 2 gluons. What is the difference between those? Same Wilson.
So these are the Fs, and these are the gauge links which run the other way. So this is the +-, and this is the
direction.
Yeah,
That was what?
Of the arrows of the
gauge
particle number.
Because I'm looking here. Because of ABC, FABC or
no,
It's
so
basically the complex conjugate. You
Yeah.
can change it with the arrow going the other way.
yeah,
So
it
but
is
why
like
is it important? Is Sievert's TMD is not real?
well, you
It's
can
not.
define it to
Right,
be
defined
real.
this way,
Yeah.
it's not necessarily real.
Yeah, it's just odd under the
all
interchange.
structures, they DABC and FABC are
This one is related to the DABC, and this one is related to the FABC. But it's not so clear, so obvious to see that, but you can take a moment and then you can show that. But this is, yeah, but it's clear that the ++ that is not related to the +-. So you probe some, and this covers a whole area here, but the other one doesn't.
So it's purely imaginary, you say. It's take imaginary, take.
No, it's odd. So so the function is real.
So is this kind of like Oderon? So it's quark scattering, quark exchange.
Okay, that comes now.
There is no fork here.
This gluons. Yeah, so wait, the other one is next page. So we have this +- correlator, and if you take a small x limit, you can show that it is this tensor structure times the Wilson loop matrix element, which I think is a small x people will say, yeah, obviously, because they usually take here the trace, and yeah, that is in this G2 function. We'll see it later. Yeah, but it actually applies to any gluon polarization, this relation. So, but if you then take this, yeah, what is called a D-type, so ± gluon sievers, it is in the parameterization of yeah, the matrix element of this operator, which is Oderon operator.
So the U box is that the dipole?
Yeah.
Yes.
Yeah, but including the pieces. Yeah. And this is the imaginary part of that, and yeah, that determines this thing. And so, but it only appears when the proton is transversely polarized. So that's why Jian Zhu called it spin-dependent Oderon. So if you go from the leading to a TMD formalism and take the small x limit, there is no Oderon in the unpolarized proton. And there is also no helicity distribution coming out to relate to your talk. So it doesn't mean it's not there, it's just not coming from the leading twist at the large X. So that is what we do. Large X analysis, leading twist, take small X limit, and then certain things don't appear. So they are probably related to things with 4 Wilson lines. But this we didn't look at yet. So this spin-dependent Alderon, so where can you measure it? So you could do that in, as I said, photon jet. But thanks, so because of some small X analysis, so especially this paper, it looks like there is a hybrid factorization at small x, so then also A sub n, the single spin symmetry, when you produce, so you take EA, polarized proton, you want to have the small x gluon in the polarized proton, so the hadron has to go backwards, so negative XF, and you want to have, you want to be in the region where it's glue scattering. Since the observable here of this operator C odd, you should have a not a C even final state, because then it's not here. So that's why you can look in backward charged hadron production. At moderate PT, you will probe this thing. So there is an observable which, well, at least in small x you can motivate it. At large x you cannot, because it's not TMD factorizing process.
So what exactly do you do?
So polarized proton, getting by the ion, doesn't matter. But you want to have small x in the polarized proton. So the produced hadron has to go backward. So this is like normally you do forward, you get small x in the A.
Yeah, small x we usually use the hybrid for the opposite situation.
Just switch it. A on polarized proton.
You could do it with P also.
Also, the A is here not relevant, but if you want to see it in glue, because we have this link structure for glue going to something.
What about A polarized P? Is that feasible?
No, that's not feasible. It's really people have looked at that, but it is really like almost microscopic rotations they can achieve. No, you cannot really polarize the light ions, yes, heavy ions.
Can we just go back a bit to your taking of a small x limit? Just to understand your statements. So, I mean, this limit is very dangerous, right? You can't just, so when you send x to 0, what do you do with your TMD definition? You have x in the exponent, and that's it. I mean, you can also relate, right? It depends on your definition of the TMD.
But that's what you do. You put x in the Fourier transformation to 0.
And that's it.
We are only left with the transverse for it.
But
you can derive it also another way, but then this is just this the piece which comes with the delta function of this.
He's not talking about evolution. So
but how can you take x to 0 without?
The mathematics experiment depends on x in the idea. The stuff depends on x in the exponential, but what matters is if x depends on the math term.
Right. So that's what I'm asking, right? So the Wilson line staple, for instance, you can tilt it away from the light cone, and that tilt can be related to x. Is that you do something like this? I mean,
no. So this is
it exactly.
You can also keep the x dependence in the matrix.
So somehow I think so. The thing on the right hand side, it should depend on x still because it evolves with x in some.
All right. Some way, right? So concern.
So
yes,
this is kind of the.
That's also move, right? It's a dipole. So that
depends on x dependence.
Right. So that's the question. And what exactly do you mean by?
It's just that's the operator.
This is at the operator. This is the operator level. So if you start to do.
Anybody dipole has a cutoff. There is no dipole without cutoff. It's divergence. So there is then dipole gamma naught with the cutoff, which depends on the organics.
But it's a result of taking x to 0, right? Hand side is already the limit. So is it like the dipole to 0?
No, I think that means it's the exponential.
So this piece. So here is officially there's a mu and some zeta, some rapidity the variable,
Right.
and what we mean is this variable e to 0.
So x is really just only in the exponent.
Yeah.
What we're doing x is only 0 in the exponent.
Yeah.
There are
Okay,
two
so it's
x's
not-
here, which are confused sometimes. One x stands in the exponent, another what you
That's
want
what
for
I said.
identity cutoff. They are
Yes.
different in principle.
Yes. Well, in
Different.
principle,
Yeah,
they're
not
different.
In principle,
They're the same, but what is the
So
result?
here he keeps rapidity cutoff the same in this formula, but explicitly in the exponential goes to 0.
Okay. And what was the statement about not illicit?
Yeah.
They are equal.
Getting to the core of the point.
Whatever rapidity cutoff is, they are equal. It's trivial. I mean,
What is it?
well, right,
Left side and right side. Yeah, no, that
Yeah.
I understand now. I'll ask
Yeah.
the next step.
sorry.
Yeah. But so if you do here the leading twist expansion, and you do leading twist expansion this one, you will see you don't get helicity contribution. So that means it is somehow in this limit, it is suppressed. So we have, say, x, this is, say, a constant, and x helicity is 0. Yeah, so this thing,
This is for polarized proton,
so this would be a longitudinally polarized proton.
Yes.
Yeah. So in your story, so you get something like this, right? For this behavior.
For G1, not X-G1.
Yeah, G1. Yes.
G1, yes, yes.
Yeah. So that is consistent with what we are finding. So we are not taking logs of 1 over x and we summing that, etc. Which will we just look at the integer powers.
Okay, so for you, 0.6 is 0.
Yeah.
And so what we
And
find
this
for
is-
you is a constant, and then
Yeah.
x types a constant, and x equals 0, limit is 0. That's what
Yeah. So this is the
Right.
same whether it is x or
Yeah, I think
X
Pete
to the
was
1.
saying something in the evaluation also that you guys are only looking at the
Yeah.
powers.
Yeah. So when I say that something is not there, it could be there, but it doesn't come from that leading twist TMD formalism. So it has to come from something beyond that.
Sorry, so then I have a question which is related to that. Because I always have issues with the way TMD people use twists. Because you have 1 over Q corrections and KT over Q corrections.
Yeah.
Which one is your twist?
Yeah, so it is this Jeffrey's working redefinition of twist. Because if you look at this operator, of course, it's the power.
Yeah,
If
so
you
that
take
would be 1
local-
over Q corrections, not KT over Q.
One is dimensionless.
What does it? M squared over Q squared?
Yeah, sure.
Yeah.
I mean, one of them is enhanced by KT, right? And I mean, these are two completely different expansions. The twist expansion requires that you have a single scale, which usually is Q.
A hard scale.
If you
Yeah.
have KT,
Single hard scale. Yes.
so you're taking KT to 0, then performing some expansion, or
No, we take KT fixed, but it cannot be. It must be much smaller than hard scale.
So there's only something Q squared is the only hard scale.
Yeah. Exactly.
It's just that there's a soft scale KT,
Yeah.
which is soft in the sense of not having a large log
Exactly.
of K, but it's different from lambda QCD in the sense that it's a vector, so you
Yeah.
can somehow look at directions with respect to the direction of K, but it's a soft scale.
But
And this direction gives you the polarization.
But what you say again, that what you look at corresponds to the twist expansion, I'm not quite sure. I mean, are you saying that what we did, for instance, is higher twist? Because we took the same operator definition. Yes, we tied the slope of the Wilson line to x.
Yeah, no. So what I mean is, so if you start to do evolution in X, then you can start to relate the thing with 2 Wilson lines to something with 4 Wilson lines. If you want to get the 4 Wilson line thing out of this formalism, you have to start with the 4 Gluon field operator, but that's suppressed with large X. Yeah.
Yes.
So it's small x. If you do the complete story, you need all twists.
Right. So, well, okay, I don't know. I'll have to think about it.
Yeah. So when I say something is 0, it is modulo. Yes.
It's not like we see any Q squared suppression. That's my concern.
I disagree here because the next terms are not suppressed by a small x. They do exist as small x in this expansion. power correction.
Yeah, no, but I think the statement is that say when we do our helicity evaluation, it's higher twist. I'm saying I don't see any q-squared suppression.
Because you compare to 0.
Right. Also compared to that.
But you,
But then-
you have
so
you have
leading
longitudinal polarization.
Leading twist is 0.
If the leading twist is 0, then
Yes.
and then you're doing a higher twist, but
without knowing.
you're doing a higher twist. You're doing a higher twist thing.
I would
But
probably
since
see some bizarrely high power on q-squared, right? Even if so if it's 0 over q-squared at the leading twist, then I would still see something over q to the 4th. I don't see no q to the 4th.
Daniel, your statement concerns transverse polarized protein.
No,
We're not talking about spin on the next
Couple of
slide.
Yes, so in this talk I only mentioned transverse,
Yes.
but
I
in
think what Julie is
passing,
talking about.
Gluons and BF.
in passing I made a statement about this function. So
So
that-
can we return to unpolarized cases?
Yeah.
It's easier because
Yeah.
everyone is familiar here, right? We take BFK evolution, right? And we can write it as evolution of dipoles, right? As we've been talking about all this week. And then, of course, your evolution, your Gluon emissions generate multi-Wilson line states, but then they don't higher twist, they're not q-squared suppressed.
Well, depends.
What do you mean depends?
No.
BFK is not, I mean, it has some higher twist contributions, but it does
But the
have
first
a little-
non-zero contribution to the 4 dipole, to the quadrupole. But non-zero contribution is the one with 4 with 4 gauge, which is higher. Of course,
if you try to quadruple, but I'm not even talking about
the same with 2 dipoles.
for BFKL is a ladder, right? So you can obviously do your evolution. So you
That's a
split
linear
the
part.
dipole in 2,
Yeah,
but you
that's
can
a linear
involve
part.
only in one of the
Sure, the BFK is the
dipoles.
linear part.
Yeah, but that's fine.
But
Helicity evolution is also linear part. So,
But
so
the decay part, the non-zero decay part, the 2 dipole scattering.
I don't think that's a statement. That's a statement is any evolution. So like what Daniel wrote about helicity, that's also just a linear part.
Yeah, but what he said in words that the dipoles come from 2 dipoles, what he had in mind was the scattering of the 2 dipoles, that's a high twist effect. Otherwise, just BFK.
But it's not a higher twist effect. We know that the dipole splits into 2
Understand, but the
dipoles and
scattering
it's
of
all
the
given
the scattering of the 2,
BFKL.
I agree. But the simultaneous, the non-linear part, the scattering of the 2 dipoles, otherwise you don't care about it.
But you don't need this nonlinear part to get
Then of course,
BFKL, right? But then that's my question.
we
Is
have.
there's a multiple dipoles, it still gives us. I thought the statement was that all small x evolution, so F1 is an unpolarized distribution, right? It's constant at the 2 gluon exchange level for us, but if you start including evolution, it's going to change this constant to just the power of x, like you wrote, but it's not going to be hard twist.
Of course.
But I think Daniel made a statement that all those deviations from a constant are higher twist.
Okay.
And that's, I'm not sure I understand.
You're asking where the logs? Logs are somewhere there.
Right, where are the logs of x? And
Yeah,
Daniel
yeah.
claims that logs of x are higher twist. I'm saying they're not.
Interesting.
And I think you would agree with that.
Logs are cannot be high.
Right.
Every
Yes,
other
so-
piece comes with a log of energy.
So again,
Every piece grows with log of energy.
Yeah, that's a
but
different
forget the
issue, of course.
higher twist. BFKL.
But also the ring is good.
BFKL has a major leading twist contribution. And if Daniel says that in making this approximation, he's throwing away higher twists and just gets a constant for unpolarized distribution instead of power of 1 over x, I'm concerned
What
because
is your problem with this?
it's against.
So is the question of whether the difference between 1 over x and 1 over x to the
Yeah.
1.3 is that the higher
Yeah,
twist
is that higher
effect or
twist or
not?
not?
Yeah. Probably not, it's not so much
Yeah.
with this, well, probably may originate with this formula, what was discussed about the slope of the Wilson line, but it translates into those statements on the board. Maybe they're on the next slide, I already forgot. Maybe
Whatever
There was a paper.
summation of logs give us, we don't call it twist. Whatever it gives us.
well, but Daniel calls it.
Yeah,
so
maybe
that's-
that
that's
is the problem, but my terminology. But
You call x to
In-
the power 1.3 next high twist? Okay, then you should warn in the paper that I'm calling.
no, we didn't say this in the paper. We didn't say this in the paper.
Because people will be
No, in the paper, we say resummation of large logs.
I think
Well,
so.
log 1.
But
Yeah, so I don't have the answer how to get from this equation this power.
Right.
But,
Or, as I
yeah.
said, it's easier to talk about VFKL as a non-slave.
Yeah.
It's not going to be a fair twist. It's not only
Yeah.
fair.
No, I
The
see,
leading part
I
is
see your
leading
point.
twist.
I see your point.
Okay, if it's not crucial for what's to follow.
Yeah, no, it's not crucial. This is just when I just wanted to say whenever I say 0 or something like that, then it is not necessarily 0. It is more below this.
Probably if you expand in operators and you see 0 at the operator level, you will see 0 with the evolution also.
It's not just tree level, it's tree and icon level. So you can also have helicity at the two-gluon exchange level, it's just not at the icon.
Euro, can you? I told
So
you that
this,
if I expand like that formally and see 0, you evolve left hand side, expand, you will not see 0. That's what I explained. Okay, again, then evolution was on the left hand side, the right hand side. And you are telling us that if you evolve, first you see without evolution, you see 0. Yes, exactly. 0. Then you say, okay, let me evolve left hand side. I evolve left hand side, then take x to 0, don't get 0. Are you trying to follow that?
I think the formula should be understood not as an equal sign, but as a limit. What he says is x g1 goes to 0.
Yeah, there's a limit.
As x goes to 0. For small but finite x, it's non-zero.
Yeah. Yes.
So you want to spoil this expansion. You want to find such
I don't
power.
want
Yes. No. And such power, such from the logs. You want to destroy this expansion. Your logs are more important than your original expansion into this.
No, I don't want to spoil twist expansion. I want to stay at the leading twist. And
Yeah, but this power,
this
power and that power can be different, of course. They can come from the same thing. But here, this is what you say. You already have an operator on which you do corrections. And here we have no operator on which we do corrections.
In a limit, right? If you really send x to 0, this is just a statement that g1 at the leading order by itself is a constant. So x g1 goes to 0. F1 at the leading order at the two-gluon exchange is 1 over x. And g1 at the two-gluon exchange is a constant. Either of those objects are non-zero, so I can evolve from a constant and get the power of 1 over x. I can evolve from 1 over x and get the power of 1 over
But so this power, you say you also get in the linear case. So you didn't need to use nonlinear evolution to get this power. Right? That's what you're saying, right?
Absolutely.
Okay.
Just like power of 1.3 was 0.3. I'm not sure why it's 0.3, probably because you're thinking analog corrections as well, but this 0.3 comes from at the leading, okay, if you take leading on the VFL, it would be, more like 1.7, 1.8, but deviations from 1 are just from linear evolution. It's not
Okay, I see your point. So, but I have no good answer. But for the rest of my talk is not relevant. But at least you know the limitations of what I'm going to say. So, so when I say there is no Odron operator in an unpolarized proton, it is also in that sense. Yeah, so everything that is not there can be there, but not from my starting point. Okay, so the spin-dependent Odron, there is an observable, I think is nice.
But I'm sorry, sorry to belabor the point, but the other one, the other one gives exactly, well, I don't know which TMD it would enter, but it certainly exists in this x zero limit. The other one gives exactly 1 over x. So x times the other one is a constant, even after evolution. And that's actually a very peculiar result, which we know that leading and next to leading order and perturbative calculations in PCD and Hamilton Sosa-Brang Mills, but also on the CFT side, there are works showing the other intercept is 0, which does mean that you're even a strong coupling, right? It's just exactly 1 over x. So x times the other goes to constant.
Yeah, but so somehow it doesn't come out here.
It just doesn't enter this
doesn't,
because you have a difference.
But the other one is a difference.
Yeah, this is,
It's
so
a process where it cancels.
it's the same operator, but you remove this ST here. That thing doesn't appear.
So what doesn't appear? You still get the difference of traces.
Yeah, but it will be 0.
But if you were doing something exclusive, you might have another one. Because
Okay, now I'm just looking at this operator.
And this
Yeah,
is
so the
fundamental.
function of x and
It's a
kt.
fundamental loop.
Yes.
Yeah.
So fundamental loop going one way minus the other way.
Yeah.
But in CGC, it's not our standard definition of that.
Exactly.
Yeah, it depends upon the way function detects the
Yeah.
expectation value, right?
Yeah.
Well, if you have dipole cut, you have another, but probably on his polarized proton, you know, the average of that, the average of the DABC gluon on that state.
One in DFKL. If you take some spin equal to 1 in DFKL, you get 0.
Yes, that's right. Yeah.
That's the order.
No, I wrote a paper, yes. But I'm not sure I understand why it's 0 here.
Depending
But
on
it
the
just
state,
doesn't
right?
appear. There is no
Take the
function
average of
that's-
the what? So you should
No, but
just
it is only 0 if you have no spin, right?
Yeah, if you have no spin. Yeah.
It's
So the
so
operator itself is there.
you have
of
no
course,
vector
but,
to drag the
Yeah.
variables.
Yeah.
You will never.
yeah, but if you do the
Yeah,
same
well,
for an
I-
exclusive process,
I know what you mean. You're saying, right, I know. The other one doesn't couple to an object which doesn't have a preferred transfer
Exactly.
direction.
That's just that.
Yeah.
Right. Yeah, very good. Because it needs to be odd under the coordinate interchange.
It's just- exactly.
And at the same time, the coupling should be scalar, so you have to dot
Dot it into something.
and you don't have anything
Yeah.
dotted.
So later
Yes.
we'll see.
Matt and I
do
saw
that.
it one time ago, just not in this language.
Yeah. Yeah, so here I say that, about the other one here I say about LST, so we discussed that. Of course, we know these Wilson loop matrix elements, they are important, small x, etc. But at large x, we don't really know how important they are. So for instance, if you have just a quark, unpolarized quark distribution, that is insensitive to whether you have plus or minus links. But you can show that if you have instead of the plus link, you loop around once more, like that, then you get something different. So apart from the fact when you have a process that probes that thing, that singles that out, if you look at that thing, it is not this thing. But we don't know how much it differs. Yeah, so this loop around this the F mu field there, we don't know how much it contributes in some matrix element of the proton.
out of curiosity, what kind of process would probe this kind of looping?
It's independent of the fact, so irrespective of whether one can isolate the function with this loop from experiment. This is so we do have processes, but not only this appears.
Sure.
So there are a bunch of other processes that have other links, and the process is questionable whether it's TMD factorizing. But you can just wonder about this quantity. If here the plus and the minus don't matter, so how much does this box matter? So you can define, again, like in Mellin moments and Bessel moments, you can define this quantity. So instead of plus, you have plus, and a minus a plus. And this you can do in the lattice. So it is on the to-do list of Michael Engelhardt, but it is a bit low priority.
So sorry, trying to answer your question, if you have two fundamental lines are in an octet state, then it's like a Gluon. So then it's some sort of a scattering of a quark with some exchanges, and the quark, icon of quark becomes an icon of Gluon. So I think one can probably engineer some sort of a two-jet production type of thing.
Yeah, but then you can always give a sum of processes. You can
For
have
Gluon TMDs, that's how we can.
Well, you ask for a
For
Gluon.
quark TMDs,
yeah, if you could ask for Gluon jet, then yeah, exactly. Yes.
I cannot wait.
Yeah. But okay, they can also look at it on the lattice, so you can just calculate it on the lattice. And
We respect this.
yeah. But so probably you can cook up something that at least is an approximator, in as far as you can get Gluon jets. But yeah, you know something about these ratios. So when this distance is 0, of course it should be 1. And when the distance gets very large, so far outside the proton, it shouldn't change anymore. So the question is, yeah, how does it go? So again, this ratio here, it goes from 1 to something flat. Well, if it is flat all the way, which it probably isn't, now then the links don't, there's no process dependence, but it can be also something like this or something like this. We don't know. So I think that is interesting to know. Yeah, so at small x, of course, with gluons, you can have something where you have only the Wilson loop, and then yeah, to have a result, it should be non-zero. And so this is.
So I already know the process. So you have diplomatic scattering, the photon comes in, splits into a QQ pair, and they interact by exchanging T-channel quarks with the target and produce a glue pair. And those two gluons.
Don't you need to have some initial state interactions too, because you have also have some.
Okay, they may rescatter iconally, and at some point there's a non-iconal scattering. So, and you produce a gluon. So, so you may have rescatterings of the Wilson lines here. Then there are some T-channel exchanges with a target. This was a proton, and then you produce two gluons which create a glue ball.
Okay. Exclusive glue.
Does it have to be exclusive? Yeah, it's yes. No, probably.
Oh, you can cook up something with open. You can also do it with open. Yeah, exactly. If you can have
but you need to trace. He needs to link it up. If you make two gluon jets, they would not be in a color singlet state. You want your two gluons in a color singlet state. You need to force them into a singlet state to be able to close your state loop.
Yeah, but then you don't have
the singlet automatic.
Yeah.
Oh, just exclusive to jet production. Okay, that's more.
Just for two jets, why nothing else? Just do two jets.
Yeah, but then the background is just quarks.
Two
Quark
jets
anti-quark scattering must be.
As long as they're gluon jets.
No, but it's exclusive. Yeah.
Yeah, but there are simpler cases. You can look in one of the papers and look at the table and just pick up this one and look up a story that you can single out that sub-process. But yeah, I don't think that is so relevant. But no, I think it is interesting to see how far this deviates from one. Yeah, so that in something that maybe looks process. And so very often it is said that quark TMDs are not process dependent, but they could be. And there's no reason why they shouldn't be. Okay. Now unpolarized Gluon TMDs. So this is a familiar story, I guess, to most people here. So for as I said before, the cases of interest are just plus and plus minus in the Gluon case. And you can have then this G1, G2, take small x limits, you have the Weizsäcker-Williams and the dipole Gluon distributions, and that solves your tale of two Gluon distributions. So that was the question, okay, we have two equally valid Gluon distribution definitions. Which one is it? Which one do we need? And the answer is, well, it depends on the process. So one process will probe this one, another process will probe that one. And that was, I think at that time, completely not obvious. Also because in the MV model, you cannot really notice the difference because you can express one in terms of the other. So you see, for instance, this process here, which you can do with the EIC. It was expressed in terms of this famous C function, so that was scattering amplitude. But this actually is a process that probes the plus. And this function is the one of the plus minus. So they've actually expressed it in the wrong one, but in the MV model you can do that. So that is okay. So there are lots of processes where you can probe them, so you can actually test. So you can see that they are different in experiment, and you can also cross-check that it is universal in this set, the universal in this set. So there are enough processes, and the EIC can do this one. So if you do photon gluon, you get WW. So I think that is nice. And then of course you can wonder how different can they be. And well, if you take a KT integral, you should get the same answer out. Naively, I would say that the large KT tails of this function should be the same, because if you take large KT, it's like shrinking this to 0. But other than that, they can be in different shapes, etc. So there was a nice study by Cyril and collaborators, where they have 5 definitions. Never mind why these 5, but so here is the G1 and the G2, and here are others which have additional loop and different traces. And yeah, the GBW model, they look like this. So the integral should be the same then, and yeah, for the tail, they found in another paper this or in the same paper.
It's different because you see this tail is calculated for the MV model.
Yeah.
Which
oh, you know this?
Yeah. Subtle difference.
If
The
you
GBW model predicts you exponentially for the function.
Yeah. Okay. So here you cannot really
So this
address this
model
question.
not,
Yes.
not seen on
Yeah, it is. That is right. Yes.
The fact that they call it a high KT isn't that a priori true because it's in a single scattering approximation.
it should be that we can show.
Yes, very
Yeah, but you have this this odd one here, which is this trace here and trace there. It falls off faster.
Yeah, in fact, we later on understood this is because it's a difference of
Two of those, yeah.
So the leading term cancels that particular.
Yeah, but but you could imagine that you have maybe a process that probes this one. And so theoretically. Yeah, but if you really go general, you can of course have infinitely many definitions with you loop around 3 times whatever. Yeah, and then what we found that is so there is a restriction, maybe not so useful in the end. It's like the supersymmetries of your symmetric extension extendable. You measure all the masses but one, and then you can predict the last mass. So that's a bit here. So if you take this, say the PT squared moment, you can show it consists of 5 pieces in a calculable way. So if you have 5 functions, you measure these separately, you can fix these independent pieces, and then if you would measure a 6th one, you can predict the PT squared average. That's maybe not so useful, but there are constraints. So you cannot, when you start to take moments, you always have a finite set. Yeah, so if you have the functions as a function of PT, you have infinitely many options, but every particular PT squared moment, you have finite numbers. So if you do PT to the 4th, you have a bigger set, but it's finite, it truncates. So it is, yeah, maybe not so useful, but it is, if you do the same thing for the Sievers, that is related to the fact that you had, so that is with 1 PT here, you have only 2 options, and that was this F and D type. That is, it was similar. Okay, then linearly polarized gluons in an unpolarized proton. So it is some interference between plus or minus elasticity gluon states. It is linearly polarized, so they are polarized preferentially along the transverse momentum, but with some cosine 2 phi distribution around it, so it's not exact. So it's not exactly that KT is along epsilon t, but there's some cosine.
Sorry, I never really understood that. So the spins are pointing along the transverse momentum?
Yeah, so the gluon polarization that is with this epsilon,
Yes.
that points along, so that has a cosine 2 phi distribution around the KT. Yeah, so if the function is positive, it is preferentially polarized along KT.
So it's the polarization you're comparing, polarization vector of the gluon with the transverse momentum of the gluon.
But it's not 1-to-1, it's saying it's just cos 2 phi
It's a cos 2 phi, yeah.
around.
Yeah. And if it is negative, yeah, then it is preferentially.
Yeah, so it's a question of so somehow you have k dot epsilon, and then
It's not k dot epsilon,
No,
it's more
but-
like k dot epsilon squared.
Yeah.
minus
something like
well, then it's k dot epsilon in the amplitude, and then the distribution is a 2 gluon, it's an a squared. So it's we times k dot epsilon squared, which is a cosine.
It's a some rank 2.
So sorry. So it's not preferentially along KT, right? It's equally probable to be in a KT direction or opposite.
Yeah,
as opposed
of
to
course.
phi.
Yeah.
And also it's relating to a first
But it's the
diagram.
direction or something.
So this is what you mean by helicity interference, because it's really like having a transverse spin.
Yeah, it is similar to that. Yeah, this is the gluonic version of that.
Right.
Yeah.
Right. So it's like sigma 1 or sigma 2.
Yeah. Yeah, in the quark case, you have plus minus a half minus.
Right. Whatever the gluonic
Yeah.
version is.
Yeah. Okay, so this thing could be there, and yeah, plus plus is minus minus here, and plus minus is minus plus. So you have two of them. It's much harder to measure. So many processes it doesn't enter. So we found a bunch of processes where it does enter, and there is only one so far known where the dipole one appears, and the rest probes the WW one.
Actually, this is true if you think of leading order. If you calculate the next leading order corrections to the processes which involve only the F and the H would appear. We realize this.
If you only
if you go to the F table, where there was no H, and you
Yeah,
start going to next to leading order, then those H TMDs appear.
Yeah. So the H's are perturbatively generated. Yeah? So if even if you say, well, the 0 at one scale, it will be non-zero at another scale, and it is driven by the unpolarized one.
Even with loop corrections, not just by the evolution.
That's the same, right? That's the same thing. If you look at the observable, it is just.
Because, I mean, the evolution is a part of the loop correction.
Yeah.
It's a leading node part of the loop
Yeah,
correction.
exactly. Yeah, but it is. I think whether you probe it in the process is still the requirement. So, say you have TP to Higgs X, and this thing is 0. Then after evolution, so alpha S squared, you will have something. Alpha S squared corrections, but the other way is not true, I think. And it looks like what you were saying, that you could add all these other processes which have F1. And if the process is not sensitive to the helicity flip, you can radiate whatever you want. It doesn't get you the helicity flip.
You say it cannot be. You say it's not difficult. It's more difficult to extract. It cannot be obtained in gamma jet production.
Yeah.
If you calculate gamma jet NLO, then it will appear.
So why can the correction bring a helicity flip? Suppose another alpha S correction knows about the mass, right? So it has a mass term.
Oh, if you start to have masses,
It will somehow couple the helicity flip observable to, of course, non-helicity
Yes, but you need a mass,
to propagator which acts like a mass and then incorporate.
No, then for sure,
I think those of us who survived to the end of Renault's talk yesterday will also have a discussion whether there is a two-digit production process which measures a leading order, measures the Wigner distribution, whether when you go to next leading order, it actually still couples the Wigner distribution, and that was not at all obvious, and probably the answer was no. But here, if you know exactly what it couples to, that's still
The gamma jet is the simplest example. You have a quark and it's a photon.
That
is not sensitive to the H group. But if you start looking at gluon to QQ bar to photon, you calculate gamma jet NLO, this is sensitive to the H.
But then
that doesn't mean that makes it easy to explain.
No.
It's better if it's there from the beginning.
Is this something different that's probed than what's probed in PP, looking at in a jet, looking at the
that's something different. That's different. That also depends on linear polarization of the gluons, but it's a different thing. Okay, so we looked at some estimates for some of these processes, and for some we only have upper bounds, and for some we have more sophisticated things. But the relevant one for ESC is this one, which I will show some plots for that. Most of these observables to probe this are angular modulations. So only in Higgs production or eta C, eta B production, it appears in an angular independent way. But so most are angular modulations. So that is, for instance, the example of ESC here. So you produce open heavy quark production like this, and then you have, of course, you have transverse momentum for each of these heavy quarks, and the sum and the difference don't have to be in the same plane. So they can have different angles. So you can look at the difference angle and look at cosine 2 phi at that. So it's not straightforward, but you can define this asymmetry, and that probes this function by itself. So actually, that could be quite large, and especially towards small x. So here are a couple of arguments why we think at small x this thing is very relevant. First is a Dietleb argument that it has the same. This is basically what Cyril was saying. So it is generated perturbatively from unpolarized Gluon distribution, and it has the same one where x grows as the f1. So as the f1 grows, the h1 perp keeps up. It grows as fast because it's actually generated by the same object. So the argument we had here with this this relation that I showed before. So if you parameterize for an unpolarized proton, you have two functions, f1 and h1 perp, and on this side there's only one function. So in the limits, these two functions should be the same. And the same means the difference is 0, and that means modulo partial powers.
Wait, but this is only true for the plus minus.
Yeah, this is for plus minus, right. Yeah. So here we didn't say anything what it was. Here we say plus minus.
But the process on the previous page is for the plus.
Yeah, exactly. But I'm now general saying why this could be large. Here is the comparison. So if you do an MV model calculation, so none of these arguments is fully solid. So this is MV model calculation. So for the dipole, plus minus, you have the bound as we expected, and for the WW you have the bound for large K perp, and something small here for Q perp smaller, and in the small K perp region it is moderately suppressed, so it is one over the log of this thing. But so what I think this means, now Larry comes in the most controversial part. So whenever I say this in the small x people in the audience, they start jumping around. To me this means that the CQC gluons are 100% polarized, because you can actually make a process that probes 100% polarized gluons. So you can also make a process where you don't probe it, and under evolution, maybe it starts to change. But the fact that you can have some probe that probes maximal linear Gluon polarization means that the state is actually maximally linearly polarized.
You just make the classical field so
that exactly. So in the classic, exactly. So classically, it is 100% polarized. Yes. I don't know what it will do under evolution. And the small x evolution. This I don't know. But I think that is some people find this crazy statement, but I think this is it's probably.
What did they say? It's a crazy statement.
Yeah, somehow there's some resistance to the idea, but I don't know why.
Depends. The statement is can be or is.
Yeah, so I put now can be to.
Can you construct a classical field?
Yeah, it should be. Yeah.
You have constructed classical.
Yeah.
Okay. Fine.
Well, MV model.
Well, you have to make a special classical field in terms of property, right?
All the polarization vectors have to point reaching
Yeah.
each point transfer.
So in that way, I didn't
point
look
in
at it.
same direction.
But in some sense, it's a pretty generic feature in any classical field. It just what the full polarization with this 100% polarization just means is that the gauge field AI is a derivative of something, and this is what you get when the gauge field is obtained from an equation by an equation of motion from a color source. Then you always get this.
Yeah. Yeah, I agree with that. I think so. This is also true for photons.
Well, for an arbitrary color source, it's randomly oriented as polarization.
No, but it's a derivative. So somehow the statement here is that this follows from the fact that AI, the transverse gauge potential, is a derivative of some function.
But what does it mean polarization? Because I'm lost. How do you succeed?
The polarization is just the direction of the vector AI.
But
The
is it random?
gauge potential
It's like this. So
But it's not a derivative, it's UD. It's not a total.
yeah, so this is why the reason why at small kt you don't have the polarization. At large kt, so at large kt, at large kt when you linearize, then it just then the u dagger diu becomes just a derivative of some scalar function, and then you get this 100% polarization.
so this was the statement. So if you have the
generic.
yeah, so for plus minus, you can see it like this. So you have plus minus, and these ij, they give you the photon polarization, gluon polarization. Yeah, this is epsilon I, epsilon star j, or something like that. And if you take this limit, you see that it becomes proportional to kti, ktj. And that is maximal polarization.
So the way I understand what Thomas is saying is that if I take a large KT limit, my field is really just a single gluon. And the single gluon in light cone gauge, gives you K curve over K curve squared. So it's always proportional to K curve. So the direction of A field is in the direction of K curve.
Yeah.
But
That's not really the interesting limit, because that's the high KT.
Right, that's not the
That's not really
separation.
the CGC.
It's not the CGC. It's
That's
not
not
like-
what the CGC is interesting.
Yeah,
Somehow from the CGC point of view, somehow the 100% polarization is somehow the natural dilute in expectation, and the non-trivial thing that's associated with saturation is the deviation from that. That's an interesting thing.
Okay,
That's where the interesting physics is.
That is fine, but that is that's I understood at an eta of 20 or 30 or whatever. So if you have MV model, the idea was the same with if you have this ultra-relativistic electron. And the photons, the effective photon field you see from that is also 100% polarized, unipolarized.
So you take
Yeah,
so
for QED it's exact, because for QED you don't have,
Exactly.
you don't have saturation.
But in the classical case here, it is the same. So the MV model has that feature.
I think you guys are agreeing.
We are agreeing.
No, you're agreeing because you're misunderstanding each other. You're saying only a flash KT, and Daniel was saying that in the MV model of any KT, okay, maybe a very small KT has some,
some
suppression, but it's still largely polarized.
No, so in the MV model also this is it's a large KT.
But that's not what Daniel was
No,
saying.
but I'm saying, I said something in addition. I said that it depends on the process.
This is the statement in the first slide. In MV model, you have no polarization.
So these two things are 100% polarized.
At large KT.
Yeah.
But not at small KT.
Then we agree.
Yes.
But there is a process that probes plus minus, where it is for all KT.
Which is
So if there is a process that sees the polarization 100%, it must be 100%
But the
polarized.
Weizsäcker-Williams ones are not.
I'm not, they're just a little bit blind.
Yeah, so that's because the Weizsäcker-Williams field, the Weizsäcker-Williams distribution is UDIU dagger.
Yeah, it goes over
UDIU
with
KT dagger.
Yeah, because
But the dipole, so here the relevant dipole, the relevant dipole distribution is KIKJ times the Fourier transform of the dipole.
By definition.
Which is explicitly always
Defined
like
yes.
that, yes. But by definition,
But it is
always
the limit of plus minus. Yeah.
right. Okay, that's
because the definition is KIKJ times something scalar.
okay. So then the statement is controversial because it depends on the
Yeah,
I think it's
if I
because
can,
it can happen in one process. You just need to find one process vector.
so if I find one
It's enough
process,
for
I
me to
put on
see
these
it.
glasses and I see it's 100% polarized. And now I take my polarized sunglasses and I don't see anything. So it's not polarized. It depends. What you see is how you look.
I understand your statement.
Yeah. Okay. Okay. But modulo small x involution. Yeah. So this is and just as a curiosity, so in the KT factorization approach, CCFM, etc., they have this all the time. This is maximal gluon polarization. They just never
Because
said it.
they are just working in the linear regime.
Yeah, they're working.
You know,
They're epsilon is
so
just
it's always
Yeah. So okay. So I think this means you can at EIC expect some large effects from this. So we have this observable that goes into phi. These are the maximal possible. Let me not explain all the variables. Yeah. So this is the transverse momentum of the large of the heavy quarks. This is for charm, and for bottom, the maximum is more or less the same, so 15% asymmetries. Where it peaks depends on the details, but it's Q squared independent, more or less, the maximum. We also did, since it is a process where you have WW, you have to worry about that small k-perp region, so we also did looked at this observable in the MV model. And then you get some smaller asymmetries. So now it's plotted as a function of the transverse momentum of the pair. But the bound here would be something like 12 or something. So it is smaller than the bound, but it is still quite sizable. Yeah, so I think this is a nice observable to look at the EIC. You can also look at it in dijets. And this was, for instance, studied here by some people present here. Found large cosine 2 phi's also. This was recently studied by also Thomas Ulrich and collaborators to see if the dijets are actually good approximators for your parton level asymmetry. And in QPerp, that looks to be, yeah, you were going to talk about that.
I don't want to talk about V3 though.
Okay. Okay, so well, it looks so in K-perp it is a good approximator. So partons versus the reconstructed jet. In P-perp there is some shift, so I don't know. Yeah, it looks like this is also feasible.
So it's because we lose something there when we do the jet construction.
Yeah. Yeah, but I don't know if you can correct for that then. If you know it, maybe it is correctable, I don't know. But there is also an interesting statement in this paper's observation that if the photon is longitudinally, transversely polarized, you get an opposite sign for this. So I think this is very interesting to check.
So this is true for vertical scattering of electrons off the Gluon field of a proton or nucleus with equivalent electron pairs. You should see this in E plus E minus pairs when you scatter a photon off the Gluon field, because that's why it's Williams.
Yeah, but this is EA. EA scattering.
But you're just scattering off the Gluon field.
Yeah.
Which is
From the
charge,
and the A, yeah.
That should be the same, right?
Yeah.
So there should be an effect which you should be known in electron scattering. QED.
Oh yeah, so yeah, the QED equivalent has been studied.
They've seen it experimented.
This I don't think they look at exactly at this, but
the magnitude of this cosine to phi is proportional to Q squared.
It was studied, I think, theoretically mostly because for photon colliders.
Mm-hmm.
Photon going to Higgs and trying to see if the CP ought to CP even or something like that.
Okay.
But yeah, that is 20 years ago. Yeah, but I don't remember the details there. Yeah, but there is definitely everything here. There's a QED analog. That's for sure. Yeah. Then one more observable is that you can, instead of having open heavy quarks, you can have also bound heavy quarks. So you make a J psi or an epsilon. Then you can also probe this function, but it turns out that it depends on if you get this color octet long distance matrix elements in. They are not very well known. So we suggested that you can take some ratios of symmetries with it polarized, etc., to cancel out these long distance matrix elements.
Ratios of symmetry.
Yeah.
They're not going to like this experiment.
Well,
It's probably not for them.
yeah. No, this is ratios of ratios is something. But I think they may not dislike it because it cancels out more systematics, etc., systematic errors. But okay, it is complicated. But then we thought, hey, you can also turn this around. Instead of trying to study the TMDs, you can study these long distance matrix elements. So if you compare the bound cubibar to the open cubibar, and you take again, well, there's some ratios here. It goes into phi ratios or the phi integrated ones. In this analysis that we did, you get two observables with two unknowns. So these color octet long distance matrix elements, which you can then isolate. And if you can, in addition, look at the polarization states of the quarkonia, you get two more equations with the same unknowns, so you can double check.
So that's for moderators.
Yeah, yes.
At low X, you would expect some singlet contributions as well. Then that would be less.
But why?
Well, because you can include multiple scattering, which would target on the singlet. Well, here, the reason why you have octet is the bidding transition is just the amount of the bar with one glue in each one. If you start having multiple scattering at low X, you might also have the amount of Q bar in the singlet with singlet.
Yeah, so at large X, that will be, it has some suppression in RQCD
you can
language.
you can project to singlet and multiply it by the singlet.
But that somehow.
But at moderate X, when you have one glue, you not projecting one glue on
so at moderate X, if you only have one gluon, you have to be in the octet. At small X, you can have more gluons, but still the octet dominates by an NC. So the singlet is just NC suppressed.
True, but the LDMEs are also suppressed octet when compared to the singlet. Depending on the KT of the quark, it's a mess, I must say, for me. But in some cases,
I don't know if this is spoiled with small X. I have to think about it. Okay, that is my last piece. Maybe I can try to finish that in 10 minutes. So the GTMDs.
You don't have until 1.
No. No, I have 4 more slides.
Okay, I'm just making sure we don't get kicked out.
Okay, 2 minutes per slide. So people have looked at the GTMDs, so generalized TMDs, which basically means off-forward TMDs. And those are Fourier transforms of these Wigner distributions. So here are the TMDs, so they are GTMDs, X, KT, and this forwardness. And then this is the Wigner one with KT and BT. And of course, you have now 2 vectors. So KT and BT are not Fourier conjugates. So you can have distortions in the BT plane depending on KT. Here's an example by Dorsey and Sweeney, and vice versa. It's related, you can relate to angular momentum. Okay, this you can have for quarks and you can have for gluons. So this talk was about gluons, so focus on that. So there was the first suggestion to measure these gluon GTMDs in EA collisions going to hard diffractive dijets. Which is an extension of an earlier suggestion to probe gluon GPDs. But the point is that in this discussion, again, there is always like the Wigner distribution and the gluon GTMD, but of course there are several, even for an unpolarized proton. You have 4 independent ones and they are complex valued, so you have basically 8.
So these are 4 independent components of one operator. In that case, you have the trace.
But depends on the operator. We have open indices. So.
Yeah. So I mean, it's just the index decomposition of one operator, right?
Yeah. So I have it. Do I have it?
Enter operator.
Yeah. This one.
Yeah. Okay. So
So we have. This is for the dipole. That we go here. So we have 2 of these indices, like we had before. These are the gluon polarizations, and so you can decompose it into 4 functions, complex valued. And then you, in the forward limit, you get this dipole thing, which goes in small x to the Wilson line. And here you can have, in small x, you go to a Wilson loop GTMD. And there's the point is, this is parameterized with only one function. So at small x, there's only one. This E. And just like here. Yeah, so that is, I have it in the backup slide here. Yeah, so we have this thing, depends on the two links. We have polarization. So at large x, it will be these four things, which are complex. And at small x, the tensor structure will be multiplied, this one thing that you were mentioning. So that is here the forward matrix element of this Wilson loop. So that means a relation at small x between these four functions. And what people discuss in this paper on the hard refractive digest, you see II. So that is the trace. So that is this thing, the F1. Of course, in the limit, F1 is related to this.
And then, of course, for each F, you have different Wilson staples.
Yeah.
To make it even more fun.
Yeah, to make it even more fun. Yeah, exactly. Yeah, so in this process, it is plus minus, if I'm not mistaken. Yeah, and of course, here the imaginary part is again this Odron thing, which, as I claimed, was for the unpolarized proton was vanishing in forward limit. And yeah, so and what people call the elliptic Wigner distribution is the cosine 2 phi piece of that thing, or that thing. But if you are at large x, any of these four functions will have an elliptic piece. And the cosine phi piece is then related to this Odron thing, because you have to have this minus sign, you go delta to minus delta, a to minus k. Yeah, so it is related to odd harmonics. So this is the point I want to make, and then I'm done. So we have this function here. So normally in GPDs, this delta it only comes from the off forwardness. But now you can have, if you look at the nucleus, you can have two sources of B dependence. And the position of the operator with respect to the center, so this is the transfer center of longitudinal momentum that Matthias Torkart is also talking about, or used to talk about, I don't know. But there's also a nuclear profile, which is also a function of B.
These are not the same B, right? I mean,
so the first one is with respect to the center of the nucleon, right?
Yes.
So this is kind of the transfer structure at the scale of the size of the nucleon. And then the other one is the transfer structure at the scale of the size of the nucleus.
Yeah.
So, but that's kind of what I mean. I mean, you have the physical B, which gives you the distance between projectile and the average position of the nucleons in your target.
Yeah.
And then you have the profile around this, but this is kind of a new R. It's not a B. It's really, it's a B minus B star.
Depends on what you mean by B and R.
Yeah, but it is the conjugate of this dependency.
So what I mean is usually if you're at low x, in Lycan perturbation theory, you have always factorization between B dependence and R dependence, because everything is transverse boost invariant.
Yeah, so the R is the conjugate of KT here.
So once you...
Sorry, why do you have factorization between B and R dependence?
Transverse boost invariance, your wave functions depend on R, right? Transverse boost invariance.
What is R?
You don't factor, you don't have B.
I mean, you take E and News.
But the target
Solution of BFKL for non-forward case. We have factorization of B and R.
To have transfer, what you call transfer. So what you call transverse boost invariance is translational invariance in the transfer plane. That's only true for an infinite target. It's only true when the target is infinite to transfer plane.
Delta is zero.
Delta is zero.
Yes, exactly.
That's not what I'm saying. I'm saying if you're writing a profile of your target, you're saying the target is roughly at some average B, which is B star, and then you have some wave function profile around B star, which would be dependence in B minus B star. And these are two different variables.
Interaction is not the interaction between two onia does not factorize the impact parameter and the sizes of the onia. because it's described by
Sure.
E and new functions in the FPM case, which
And you're okay. So you're putting those two together.
I'm not sure what your objective
Okay,
is.
no,
what
that's
you're
fine.
saying.
So it's not so important, but so I just wanted to say here that thanks to this profile, you can have in the nucleus, you can have this Odderon operator that we didn't have before. And that is related also to this paper of Edmond, where you look at the, so this profile gives you some inhomogeneity.
We introduce a new vector on the transverse spin. Instead of the spin that
Yeah.
before, it's the impact parameter.
Yeah, exactly.
Yeah, no, they're always there.
So you feel this mostly at the edge of the nucleus, where it changes the most. And yeah, so even in this forward limit for the nucleons, you would have now some Odderon effect here, because you keep on having a delta. And so you can have, well, you have this Odderon, and you can look at the process, and you get odd harmonics from this effect. And it is different from having a nucleus that is anisotropic in the azimuthal direction. Sure. And so you have that it is inhomogeneous in the azimuthal direction or in the radial direction. And the one in the radial direction gives you already this Odderon contribution, giving you odd harmonics in some processes.
If you later integrate on this impact parameter, you lose it, right?
Yeah, that's why you find Odderon squared effects, but it nevertheless enters as an odd harmonic in the final observable.
Well, you may also have the Odderon multiplied by some other quantity. For instance, a long time ago, Matt Sievert and myself, that was Matt's very first paper, where we looked at a new channel to generate a single spin asymmetry using the Odderon. And the Odderon coupled ultimately, there was a transverse spin there, so you didn't have to square the Odderon to get something non-zero.
Yeah, I didn't put the reference here, but in the paper there is a reference. So
I'm not saying
no, but we use the same thing.
But it's very interesting. I never actually heard the discussion. So people look for Odderons for a very long time, but no one actually ever realized that if you just have an unpolarized particle like a proton, and you do some sort of scattering on it with not a spin-dependent observable, the Odderon would never really come in.
Yeah,
at least the standard perturbative one that we like. So,
but in the nucleus you can,
unless somebody heard it.
But
it's not after you have to integrate the relevant parameters, it will go away, right? So if you have
no, because you have Odderon squared.
Right, the Odderon squared level.
Yeah.
But at the linear level.
Yeah, then it's everything. Yes.
But do you have something that, I mean, if you measure linear stuff, you can have linear level?
No, we didn't find such an observable.
And you could think of centrals, right?
Like gamma star 2 with us.
Well, like I said, you can have Sievert's effect in PA, which is linear in Odderon.
Yeah. But then we call it a different Odderon. Right? It's a spin-dependent Odderon.
Oh, you're looking for your spin-dependent. Right.
That's the spin-independent. Yeah, so I want to have an observable for the spin-independent Odderon.
Ours is spin-independent. Target was unpolarized.
Yeah, I agree. This is unpolarized.
Okay.
Completely unpolarized, but my point is it appears only thanks to this nuclear profile.
Yes.
Yeah, so in the proton we wouldn't have this thing. That's
also
I mean, the proton also has some profile.
Yeah,
okay, this is not.
Proton
It is not in what we were doing.
Yeah, actually, the gradient, I mean, the proton profile is much steeper, whereas we get much smaller length scales.
Yeah.
So somehow the gradient in B is much larger for a proton
that is true.
than it is for a nucleus.
Yeah, but it is nevertheless somehow to get a factorized expression for protons with the profile is a problem. It's difficult. Yeah, so it is. So if you do anything with collinear factorization or TMD factorization, you cannot have a profile of the proton.
Yeah, because if you want to do this kind of factorization, you're always treating exclusive and inclusive processes in some different.
It is
different way.
Yeah, so
it's a whole different.
Yeah, but in practice, of course, there will be profile.
Yeah, if you think of somehow the physics.
Yeah, but I don't know.
Gradient is much larger for protons.
Yeah, that is true. Okay, I think this is it. So let me conclude. So yeah, the TMDs are all process dependent, and there are lots of observables where you can test that and see the systematics, because many things are, so they are not universal, but many things are calculable. And so there is systematics. For unpolarized, there are lots of observables where we can test that. For linear polarization, yeah, there are a little bit less, but many that you can do with EIC. And yeah, you can test then whether, for instance, you have maximal linear Gluon polarization or not. I mentioned this new observable with where you can have a new probes of polar octet long distance matrix elements, which are fully known. And I mentioned that there are 4 Gluon TMDs, 4 unpolarized hadrons, and they all have elliptic-p's, etc. And in small x, they reduce to one thing. And yeah, this, for a nucleus, this allows for an overall in this setup that we were discussing. So that's it. Thank you.